Today we'll be going over factoring special cases. We can use the formulas found in multiplying special cases to factor these trinomials or binomials and separate their factors. In our previous video, we learned about the difference of squares and the perfect square trinomials formulas, where if we had some value added to another value and as well as subtracted from that same value, we can get those values squared, the difference of those values squared. In this case, we are going to be going from the end product and break it down into their factors. So we really need to understand the patterns. Number one, for the difference of squares, we're going to need to find the square root of both of our values. As of right now, it's going to be showing the square value of whatever we have. So we need to be able to work backwards and find the square root. This is the same for perfect square trinomials, but we'll also have one extra step. That center piece for both of them, after we find the value of a and b, we need to know if it is twice as much as the product of a and b. Now, we want to do this after we factor out the GCF, so it's in the simplest form. And we can see if it is possible to simplify it anymore, or factor it anymore. Looking at this first section, it asks to determine if the polynomial is a special case. If so, which one? So it's not asking us to solve. It simply wants to know, can we use the difference of squares, or can we use the perfect square trinomials, if at all? Number one only has two terms in it and a subtraction sign in between. This matches up with our difference of squares. We can find the square root of anything with a power, and if we know how our square roots work, we know that the square root of 16 is 4. Since we have whole numbers there, we can use the difference of squares rule. I did write an F there. Difference of squares. There we go. That makes so much more sense. So I'm just shorthanding it to make it easier to write it all out, so I don't have to repeat it over and over. Number two, it shows that we have an addition and a binomial. We only have two terms. None of the three formulas have only two terms and addition. This one has a subtraction. So this one is not a special case. Now with our trinomials, it's a little bit more difficult because we not only have to see if we can find the square root of the end, but we also have to check that middle step. To make this a little bit easier, I can label what my A value would be as well as my B value, so that I don't have to remember it. I can keep it to the side. For number three, the square root of 9x squared, I would square root the 9, which is 3. And the square root of x squared is x. So my A value would be 3x. For B, I'm looking at the 4. The square root of 4 would be 2. So I know they come out to whole values, terms that I can deal with. But now I need to see if they will combine and double to equal the negative 12. In this case, the 3x times the 2 would give me 6x. And if I multiply it by a negative 2, following the second formula, I would end up getting the negative 12x. So in this case, it works. It would be my perfect square trinomial. More specifically, it would be my difference perfect square trinomial, because I had to use the negative sign for this. Number 4, more than likely it could be the perfect square trinomial. It's the same one, the difference. But we need to make sure. One clear indicator is this is an odd number. And following our rule, since we're multiplying this by 2, it's going to have to be even. So that kind of gets rid of it. But just to make sure, check all of our work. Our a in this case is the square root of x squared, which is x. Our b for this problem, yet again, the square root of 4 is 2. So if I were to do the same trick, it'd be x times 2, which is 2x, and then I would have to multiply by a negative 2, which would give me a negative 4x. That is not the case. So this is also not a special case. This would follow one of our regular rules. Now to work it fully out, if I look at this one, example 1, it has 2 terms and a negative in between. This is pointing towards my difference of squares. So first I need to see if I have square root values. In this case, square root of x does come out to a solid value. The square root of 16 we checked earlier, it also does. So this is the same as number 1. We know this is a difference of squares formula. Now what this means is if I want to completely factor it out, I'm going to follow the original portion of the equation. I'm going to follow the first expression. I'm going to have the sum of a and b and the difference of a and b. So the sum would be x plus 4 and the difference, if I can write this parentheses a little bit better, would be x minus 4. So for the people who've been following along and saw the videos before where we have to actually factor everything out, this can save us a lot of time and effort because in the original video we had to find what factors add up to equal the middle. In this case would be 0. We then have to plug those in and then factor out twice in those terms. Whereas here, once we figure out what a and b are, we can simply write down the original pattern, saving us a lot of time. Example 2, now it's using the 3 terms. We have a negative on the middle. This is our perfect square trinomial using the negative. So I know I'm going to have the difference of a and b, and I'm going to square it. So the special case was perfect square trinomial. I already showed that my a is 3x. And I showed that my b was 2. You would have done this originally like we did earlier, and then we would have checked if 12 works. Now the completely factored form, we check on the equation again. It shows that all we need is the difference of a and b squared. So my a is 3x. Finding the difference means subtract. My b is 2. And I will square my expression. So, as you can tell, this makes my work so much easier. I don't have to fill out this entire area with all the work required to factor out my 2 terms. In comparison to multiplying polynomials, this saves me a lot more time.